Hardness test. Hardness is defined as resistance, indentation. It can also be defined as resistance to localized plastic deformation. It has several definitions. So before going into the definitions, we just move into the introduction of hardness. So this is one of the methods to characterize mechanical properties of materials. This is very rapid and accurate as well as economical way to characterize the mechanical properties of materials. Hardness is related to the tensile strength of that material. It can be also related to the fatigue resistance as well as wear. So this hardness is non-destructive testing method to characterize the mechanical properties of materials. We have seen the tension test, torsion, impact. All these are the different tests to characterize the mechanical properties of materials. In evaluating the mechanical properties, the specimen has fractured. So these methods are destructive in nature, whereas the hardness test is non-destructive. It does not destroy the sample or the specimen. So this is one of the advantage of hardness test when compared to other mechanical property tests. This hardness, it is also used to estimate the tensile strength of the material. This hardness test, it is also used as a quality control in manufacturing process. Because of its several advantages of its non-destructive testing method, its rapid way of testing. So these are certain advantages which makes hardness test best suited for quality control in many of the manufacturing process. Now moving into the various definitions. So hardness can be defined as resistance to indentation. When an indenter is forced onto the surface of a material under applied load, it causes an indentation. So the resistance to indentation is defined as hardness. Harder material resists more to this indentation, whereas softer materials results in a greater impression or greater depth of the indentation mark. Thereby the hardness is less for the case of soft material. So there are various branches of engineering. So each defines hardness according to the branch of engineering. For example, for the case of a machine engineer, defines hardness as resistance to cutting, whereas the case for a mineralogist defines hardness as ability of, it is the resistance of the material to scratching. If a material is harder, it resists scratching. And for the case of a design engineer, it is resistance to flow stress. And for the case of a material scientist, it is resistance to indentation. So this has various meanings, but all it is related to resistance of the material to flow stress, resistance to indentation if it is indented by means of an indenter. So these are some of the definitions for hardness depending upon who defines hardness. This hardness test, it depends upon the various factors, various attributes of the material. Example, the chemical composition, microstructure, grain size, etc. So there are number of hardness tests depending upon the way the material is tested for hardness. Depending upon the way the material is tested for hardness, how the hardness is measured. So among these, the three types of hardness measurements are, the first one corresponds to the oldest type of hardness measurement, that is scratch hardness test. Second, it is rebound hardness test. Then the third is indentation hardness test, where in the case of indentation hardness test, an indenter which is having either a spherical shape or in the form of a cone or in the form of a pyramid, it tries to indent on the surface of that material under the application of a known load. So the depth of the indentation or the dimensions of the indentations is measured, and that corresponds to the hardness. So various examples of indentation hardness tests are Brinell hardness, Rockwell hardness, Vickers hardness, etc. So before going into detail the various types of hardness, first we look into the oldest method of determining the hardness, which is known as scratch hardness test. It is the ability of a material to scratch another material. If a material is very harder, it resists scratching. A softer material, it shows less resistance to scratching. So this scratch hardness test is of more useful for the case of mineralogists when compared to material scientists. So this is first devised by a German mineralogist known as Friedrich Mohs. Friedrich Mohs in the year 1822. He is the person to devise this scratch hardness test, depending upon the ability of a material to scratch another material. A harder material, it scratches a softer material. So depending upon this, he devised a scale which has numbers from 1 to 10. The scale indexed from 1 to 10. 1 which stands for the soft materials, and it goes on increasing, and 10 is for the hard materials. So 1 stands for talc, 2, rank 2 stands for gypsum, 3 calcite, 4 fluorite, 5 apatite, 6 feldspar, 7 quartz, 8 topaz, 9 corundum, and 10 diamond. This is the hardest known material to man. So these are the different ranks depending upon the ability to scratch another material. So the softest is talc, which is ranked 1, 2 gypsum, 3 calcite, 4 fluorite, 5 apatite, 6 feldspar, 7 quartz, 8 topaz, 9 corundum, and 10 diamond. So these are the various minerals which are placed in this scale depending upon the ability to scratch. But one disadvantage of this Mohs scale is the intervals, they are not widely and equally spaced. For example, the interval between 9 to 10, it is very high when compared to 1 and 2. The gap between 9 to 10, the range between 9 and 10, it is more wider when compared to 1 and 2. So for the case of metals, this is of limited usefulness. Why? Because this is more qualitative in nature, and the intervals, they are not equally and widely spaced. For the case of annealed copper, it falls between 2 and 3, annealed copper. So for the case, a test material, if it scratches a mineral among these ranks 1 to 10, suppose annealed copper, it is able to scratch gypsum and unable to scratch calcite, it is placed in between these 2 points, between 2 and 3. It indicates that this test material, annealed copper, it is able to scratch 2, rank 2, that is gypsum, but it is unable to scratch 3, that is calcite. So it is placed between 2 points. First point indicating that the test material is able to scratch this mineral, that is 2, whereas it is unable to scratch this mineral 3. Whereas for the case of iron, 0.1 weight% carbon, it falls between 3 to 4. And for the case of tool steel, it is between 7 to 8 for the case of tool steel. So a material with the lowest rank, it cannot scratch a material with a high rank. It means that quartz cannot scratch topaz because topaz is higher, harder. It is of higher rank. It is harder than quartz, whereas quartz can scratch feldspar. So this is how the minerals, they are ranked in this Mohs scale depending upon the ability to scratch. So this is known as the scratch hardness test. So this test, it is not widely used for the metals, but still a form of this test, it is used for certain applications. For the case of hardened steels, that is known as file test. A file which is in a tempered condition, which has certain hardness value. So if this file scratches the test material, it means the test material is softer than the file. If the file is unable to scratch the test material, it means the test material is harder than that of the file. So this is only used to comparative purposes, only for comparison between the materials. And moreover, this type of test method is more of qualitative in nature. So this is not used for the case of metals and alloys, whereas it is more widely used for the case of minerals. The next type of hardness test is the rebound test. Rebound test, the example of this rebound test is Shore scleroscope, which is invented by a scientist known as Albert F. Shore in the year 1907. So this is one of the hardness testing method which uses the principle of elastic rebound, invented by Albert F. Shore in the year 1907. So this Shore scleroscope, it uses a diamond tip hammer which is enclosed in a glass tube. The diamond tip hammer of diameter 1/4 inch, 1/4 inch dia, and length of about 3/4 inch, 3/4 inch dia length. A diamond tip hammer, the tip radius, it is about 0.01 inch radius. The tip of the radius is 0.01 inch radius, and this diamond tip hammer, it is about 1/4 inch diameter and the length is about 3/4 inch. It is allowed to fall from a known height, from a certain height. So this hammer falls under its own weight onto the test specimen and it rebounces to a height depending upon the hardness of the material. If the material is harder, the height of rebounds is higher. If the material is softer, the height of rebounds is less. So this hardness can be determined by means of a scale which is graduated from 0 to 100. So that height of rebounds, it is determined from the scale which is read as the hardness of the material. So the main application of this Shore scleroscope is it does not give any impression or mark on the specimen. So for certain applications where the impressions or marks cannot be tolerated, this test can be used. Moreover, this test, it is also used to determine the hardness of material which is very large, for very large forgings, as well as when the quality checks, number of quality checks, they are to be conducted on large samples. One uses this Shore scleroscope test, because this is very rapid way of determining the hardness, and even for very large size specimens this can be used, and for the number of specimens also it can be used. But the hardness, it cannot be determined for only one way, that is for only one rebounds. One cannot determine that this is the hardness of that material. Number of measurements have to be conducted. Number of rebounds is not on the same place where the hammer strikes or falls on the specimen. Once the hammer strikes the sample surface, to the next surface, again the material, it is to be tested, and the average of this hardness values are to be taken into account in order to get accurate test results. So this is known as the rebound test. This is also known as the dynamic type of hardness method. The example of this is Shore scleroscope. The third type of classification of the hardness is indentation hardness, where in the case of indentation hardness, an indenter which has either a spherical shape, indenter which is of spherical shape, or which is of cone shaped, or in the shape of a pyramid. This indenter is forced under the application of known constant load onto the surface of the material or onto the surface of the specimen. So this indenter makes an impression or indentation on the surface of the sample. So hardness is determined by the formula given by hardness is equal to the load divided by the surface area of indentation or depth of indentation. So in the case of indentation hardness methods, either a spherical type of indenter or conical shape of indenter or pyramid shape of indenter, it is used. This indenter, it is allowed to indent on the surface of the specimen under a known constant load. So after equilibrium is established, the indenter and the load are withdrawn and the dimensions of the indentation are measured. Indentation or the impression created by this indenter is measured. Some hardness tests determine the area of indentation, and some hardness tests, they determine the depth of indentation. For the case of Rockwell hardness test, it measures the depth of indentation. Whereas the case of Brinell, Vickers, they determine the area of surface area of the indentation. So this is the basic principle of indentation type of hardness. So the example of indentation type of hardness is Brinell, Vickers, Rockwell. These are some of the well-established indentation methods to determine the hardness of a material. Now we shall first see about the Brinell hardness test. Brinell hardness test, which is invented by Brinell, J.A. Brinell, in the year 1900. So this Brinell hardness test, it uses a spherical indenter of diameter 10 mm. 10 mm hardened steel ball is used as indenter. So this hardened steel ball, under the application of load, it indents or it makes an impression on the surface of the specimen. Once the equilibrium is established, the load and the indenter, they are withdrawn. Then the dimensions of the indentation are measured. Brinell hardness number is given by load divided by the surface area of indentation. Surface area of indentation. So it is given by the formula P by pi d by 2 into capital D minus root over d square minus small d square, where P is the load in kgs and capital D is diameter of indenter, that is known 10 mm, and small d is dia of indentation. So Brinell hardness has the units of kg per mm square. So in order to derive the formula for the Brinell hardness number, which is load divided by the surface area of indentation, BHN is equal to P by pi d by 2 into capital D minus root over d square minus small d square, we consider this figure. This is the diameter of indentation, small d, and this is the diameter of indenter, that is capital D, and this is of height h, and this distance is x. So according to the formula, Brinell hardness number is equal to load divided by the surface area of indentation, that is given by pi d h. The surface area of indentation is pi d into h. H is the depth. Pi d into h. Surface area of indentation is given by pi d into h. So h can be written from this figure. H is equal to capital D by 2 minus x. So h is equal to, from the figure, it is capital D by 2 minus x is equal to h. So by considering right angle triangle, this is OCB. By considering this right angle triangle OCB, we have x square plus, this is small d by 2, x square plus d by 2 square is equal to capital D by 2 square. From this, it can be written as x is equal to d square minus capital D square root over by 2. This is x. Now substitute the value of x in this equation, which is 1. So h is equal to capital D by 2 minus x. X is root over capital D square minus small d square minus small d square by 2. This is h. So the surface area of indentation is pi d into h. So it is pi, the surface area of indentation is pi d into h is equal to d by 2 minus root over d square minus small d square by 2. So this can be written as pi d by 2 into d minus root over d square minus small d square. So this is the surface area of indentation. So Brinell hardness number is load divided by, P is the load divided by the surface area of indentation is given from this formula, that is pi d by 2 into d minus root over capital D square minus small d square. So this is the expression, and this is how we derive this Brinell hardness number. That is, the formula for Brinell hardness number is load divided by surface area of indentation. This is how we arrive at this expression. But there is one small complication in Brinell hardness number. That is, it does not take into account the mean pressure or the average pressure between the indenter and the material. So this does not give the correct values because it does not consider the average pressure between the indenter and the material, because it takes into the surface area, concave area, into consideration. It considers the surface area of the indentation. So by considering this surface area, the average pressure is not taken into consideration. So a more better way of determining the hardness is load divided by the projected area of indentation, which takes into consideration the mean pressure between the indenter and the material. This is given by Mayer. So Mayer states that mean pressure between the indenter and that of the material is given by load divided by the projected area of indentation, not the surface area of indentation. Average pressure between the material and indentation means, suppose if you press on your hand with the thumb, the pressure felt at the center is greater than at the edges. That means the pressure felt at the center is greater than at the edges. So in considering the pressure, one has to take the average pressure. By considering the surface area of indentation, this has not been taken into consideration. Thereby, a more better way of defining the hardness, which is given by Mayer, is load divided by projected area of indentation, that is pi d square by 4, which takes into account the average pressure or the mean pressure between the indenter and the material. So according to Mayer, hardness is given by Mayer hardness is load divided by the projected area of indentation, that is pi d square by 4. So Mayer has shown a relationship between the load, which is indicated by the symbol P, between the load and diameter of indentation, that is P is equal to C d to the power of n. This is known as Mayer's law. This is known as Mayer's law, which shows the relationship between load and dia of indentation, where C and N are constants. They are the constants for a material. P is C into d to the power of n. So according to the Mayer, for indenters of diameters d1, d2, d3, indenters having different diameters d1, d2, d3, the indentations produced by these indenters for the same load, the load is same, there is no change in the load, but the diameters of indenters are different. So the dia of indentations produced are d1, d2, d3. Then this law can be written as P is equal to C1 d1 to the power of n1 is equal to C2 d2 to the power of n2, and so on, according to Mayer. So Mayer has found experimentally that n do not depend upon indenter. The the constant n, it is independent. It is independent of the dia of indenter, which is capital D, diameter of indenter. But C and D are inversely related. C and D, dia of indenter, they are inversely related. So this is according to the Mayer's hardness, which has taken into consideration the mean pressure or average pressure between the indenter and the material. It is given by load divided by the projected area of indentation. And Mayer's law, which gives the relationship between load and diameter of indentation. P is CD to the power of N, where C and N are material constants. P is equal to C1 D1. That means when using different indenters, different diameter of indenters under the application of same load, the dia of indentations produced are D1, D2, D3. So it can be written as in this form, where N is independent of the diameter of indenter and C and D are inversely related. So we can write now A is equal to C D to the power of N minus 2. C1 D1 to the power of N minus 2, where A is constant. Where A is constant. That is C1 D1 to the power of N minus 2, C2 D to the power of N minus 2, C D3 to the power of N minus 2, and so on. So from this we can write this equation as P is equal to A D1 to the power of N by capital D1 to the power of N minus 2. So from this we can write, instead of C they are substituted A. C is equal to A by D to the power of N minus 2. So this is one of the important relationship. So this equation, it results into two very useful and important equations, that are P by D square is equal to A into D by capital D whole to the power of N minus 2. This is one useful relationship, the first one, and the second one is P by capital D square is equal to A into small d by capital D whole to the power of N. So these are the two important, the first and second important useful relationships that can be obtained from this equation. So from this it can be understood that maintaining small d by capital D constant, maintaining small d by capital D constant, small d by capital D is equal to constant. It means that geometrically similar indentations, small d by capital D constant means these are geometrically similar indentations. By obtaining geometrically similar indentation, P by small d square is constant. From that equation, it is clearly understood that P by D square is related to Mayer's law, where Mayer's law is, Mayer's hardness is given as load divided by the projected area of indentation, that is pi d square by 4. So P by D square is constant, means that is related to Mayer's law. This Mayer hardness value is constant for geometrically similar indentations. It means that these hardness values do not vary with load for the same material. If for the same material if one can produce geometrically similar indentations, then the hardness do not change with load. So this is given from this equation. By maintaining geometrically similar indentation, that is small d by capital D constant, it means that the Mayer's law is constant. It do not change with load. Mayer's hardness is constant. This is from the first equation. From the second equation, P by D square is equal to small d by capital D whole to the power of n into A, where A is constant. For different loads and for different diameter of indenters, one can obtain the same hardness value if the small d by capital D is constant. That is, for the case of geometrically similar indentations, one can achieve the same hardness values if the load or the diameter of the indenter is varied. So this can be achieved practically. I'll give you one example. For the case of Fresnel hardness test, if a load of 3000 kg is used and the diameter of indenter is 10, P by D square, according to this equation we have P by D square, that is 10 into 10 is equal to 30. So by maintaining P by D square is equal to constant, even though one uses a non-standard load which is different from the standard value, or a non-standard indenter which is having a different diameter than that of 10, one can obtain the same hardness value by maintaining this ratio as constant. P by D square is maintained constant means the pressure on the indenter is maintained constant. So in order to obtain the same hardness value for the case of a load which is different, that is 750 kg load, and the indenter diameter, it should be 5, that is 5 into 5, 25, again it results in the constant, that is 30. So P by D square is constant. The same thing is maintained here, but for different load and different dia of indenter. So by maintaining this ratio constant, even with a non-standard load and diameter of indenter, different diameter of indenter, one can obtain the same hardness value for the same material. So this is the significance of these two equations. Now I shall discuss about what is meant by geometrically similar indentations. Geometrically similar indentations means the indentation does not change its shape when the load is different or when the diameter of indenter is different. This you can clearly understand by looking at this figure. By maintaining this angle phi, and this is the diameter of indentation small d, and this is the diameter of the indenter d1. So this is the indentation that is produced, and this is the diameter of the second indenter d2, and this is the diameter of this indenter d2 small d2. So by maintaining this angle constant, similar, the ratio of this indentation to the indenter, by maintaining this ratio similar, one can achieve geometrically similar indentations. So by maintaining this geometrically similar indentations, one can obtain the same hardness values for a material even though the load is varying or the diameter of the indenter is varying. That is, P by D square is constant. It means by maintaining this small d by capital D as constant. So this is the important observation that is made, and this is given by Mayer. Even though Mayer hardness, it gives the correct accurate hardness values when compared to Brinell, the practical usefulness of this Mayer is very limited. This Brinell hardness is more widely accepted and its practical usefulness is more when compared to the Mayer. So as long as the ratio P by D square is maintained constant, geometrically similar indentations are obtained and the hardness do not depend upon load. It does not change, it does not vary with load. It is found that for the case of cold work metals, Mayer hardness, it is independent of load, whereas the Brinell hardness, it is found to be constant at low loads, but as the load increases, the hardness value decreases, which shows incorrectly that with increase, as the load is increased, the material undergoes softening. And for the case of annealed metals, from the Mayer's law, it is seen that this load, with increase in load, the hardness values increases for the case of Mayer's, indicating that the material undergoes strain hardening. Whereas for the case of Brinell, it shows that for the case of annealed metals, its hardness values first increase and again it decreases, indicating the material softening. Again, this is incorrect.